have another example of a place where decoupling might be useful. In the previous example, we had these functions that returned bool. They just returned whether or not a vector had a certain property. And we're eventually building up to cases where we're actually returning an entire new list of things. In this example, what I'm doing is accumulating a result across the vector. So an example might be, I am summing up the elements of the vector. I'm accumulating a sum as I iterate over the vector. Or I'm accumulating a product as I iterate over the vector. Or even if I want to compute the minimum element, I'm sort of accumulating something. As I go through the vector, I'm keeping track of the minimum thing that I've seen so far. So we'll run this just to prove that it works. Here we go. And the sum of v is 116. Well, that's sort of nice. And then the product is 6,000 and the minimum element is 6. And let's go take a look at the functions that I've called to do this. And maybe we're already developing a sort of eye towards seeing how we can decouple things. Now, it's a bit of a minor example because obviously these functions aren't that long, but it's worth considering how we can extract one behavior from another. So in this case, we've got the core operation, which is to, in the sum case, I want to fold in the next element to the sum. And in the product case, I want to fold in the next element to the product. In the minimum case, I want to ask a question, and I want the result, the new minimum, to be based on whether x, the element of the vector, was less than the minimum I had so far. In a sense, what I'm doing in all three cases is I'm taking the existing accumulated value, so the minimum or the product or the sum, and I am incorporating one new thing into it. So I take the existing accumulated value, a new element of the vector, and I come up with the next accumulated value. In the case of the sum, I guess we could even write it this way to make it more obvious. The sum equals the sum plus x. I take the old sum, the new element, I add them together, that's my new sum. With the product, I take the old product and the new value, I multiply them together and I get the new product. With the minimum, I take a look at the new value and the old minimum, and then I decide whether to change the new minimum or not. Implicitly, there's sort of this, which we wouldn't normally write, but if x is not less than the new minimum is just the old minimum, which of course seems stupid, so we won't bother with that. But that's the implicit idea. So my new accumulated result is determined based on the old accumulated result and the element that I was looking at. So I would like to write, the task for this exercise is, I want to write one function called accumulate that I guess uses the same loop logic as all three of these versions, but leaves the exact operation open, and I can then pass that operation in. I can untangle that in a functional sense and pass in a function to actually do the accumulation operation. All the loop logic is done outside by my accumulate function. Okay, so how does this work? I think, if I stare at this for a minute, as I said, it looks as if the actual accumulation operation is done by taking the existing accumulated result and a new element, and then performing some operation like addition or multiplication, and then taking what comes out of that binary operation, so two operands, and then storing it back into the accumulated result. And also that, unlike in our previous case, there's one other thing we have to keep in mind, which is that there's this initial value. If I'm summing up a vector, I start my sum at 0, and then I work forwards from there. When I compute the product, I start my product at 1, because obviously if my product starts at 0, it's going to end up being 0. I start my product at 1, and then I accumulate from there. And then for my minimum operation, I guess my minimum starts at the first element of the vector, and then works from there, because our minimum could be just about anything. And implicitly here, an exception is going to get thrown if my vector is empty. So if my vector is empty, there's no need for me to throw an exception because attempting to access the first element would throw an exception. In a different setting, I probably would want to throw my own exception here. In the interest of keeping the exercise relatively tight, just to this one topic we're covering, we won't worry about the weird extreme cases like a vector having 0 elements. Okay, so what I want to do is write one accumulate function that encompasses the loop mechanics of all three of these things. So it's going to work on a vector of ints, although we could use templates or something to allow us some variation there, and it's going to be called accumulate. And I should scroll down to main to indicate sort of what I want to do. Eventually, I would like to have my function accumulate take a vector, an operation, so an operation like adding numbers, and an initial value to start with. So here, if I want to add numbers, I'll make a function that adds two numbers and returns the result to encapsulate my sum operation. I might make one that multiplies two numbers or that computes the minimum of two numbers. I give it a starting point, like the first element of the vector for the minimum operation, 1 for the product, or 0 for the sum. There are a few other ways I could break this down. I'm choosing to use this one because I want a very general accumulate operation. All right, so accumulate, and then we'll take our vector, so vector of int, take it by constant reference, it's called v, and then I take some function to call. So that's going to be, well, let's see. So what do I want? I want this binary operation. It takes the existing accumulated value, which is going to be an int, and it takes another element of the vector, which is also going to be an int, and it returns an int that I will then store back into my accumulated value. So I think the signature will look like this: a function that takes two ints and returns an int. All right, and we'll call this accumulate, we'll call it binary op. So it's a binary operation. And then finally, I want an int to be my initial value. So what do I start my accumulated result at? Okay, and then I'm going to follow the loop logic of the functions I have below. So I'm going to call this result, sort of a generic name. It's going to start at my initial value. I'm then going to loop over the elements of the vector. So for each value x in v, I'm going to do the following. I'm going to say my result equals the result of my binary operation on the current result and the new element x, mirroring what I sort of have here, the current result and the value x. Or down here, I've got product equals product times the current result, the current product times x. And then here, implicitly, the new minimum will be a function of the old minimum and the value of x, although how I abstract this into my condition, how my accumulation function, will have to do that in a minute. But I think the pattern is the same for all of them. And then when I'm done, I return the result. Okay, so there's my abstracted accumulate function. I just provide a vector, something to perform, an operation to perform to condense everything down, and then an initial value to start from. Now I just need to write operations that encapsulate the various ways I accumulate things. So I'm going to get rid of these. I'm going to observe that I've decided to call them add2, mul2, and min2. Okay, so I want a binary operation, a function that takes two ints and returns an int, so add2, int x, int y. And this is a function that would get thrown in as my binary operation. Well, how do I add two numbers? Well, that's sort of easy. Return x plus y. There we go. And I notice if I sub this in to up here, I do get something very similar to the sum function I had before. I could even actually call this. I could say current result, and I could call this element, just to make it absolutely clear that that's what I'm doing. So the new result, which is what I'm returning, will be the current result plus the new element. And the same thing for multiplying two things. So I make my function mul2, and it takes, in this case, it's just going to multiply them together. And then finally, if I want to compute the minimum of the entire vector, I walk along the vector, and I just keep track of what's the minimum thing I've seen so far. So the new minimum is going to look like this. Okay, so if the current result, which is the current minimum, maybe I'll even call the parameter current minimum. If the current minimum is, let's see, less than or equal to, not that it makes much of a difference. If the current minimum is less than or equal to the element, then I guess the new minimum will just be the current minimum. And otherwise, I guess my element is smaller than the minimum, which means I'm going to return that. That is the new minimum. And so I've now abstracted out the core of each of those operations into its own special function, its own operation, adding, multiplying, computing the minimum. And now when I want to call the functions, I will switch from the version that I already had. I will switch that to the version that I commented out earlier. So here the sum of v will be the result of calling my accumulate function with my add2 operation, starting from an initial value of 0. To compute the product, I call accumulate with my vector and my multiply function starting from an initial value of 1. To compute the minimum, I pass in my vector, my minimum function, and as the initial minimum, I will start with v.at0, the first element of the vector. Now, connoisseurs will note, yes, the for each loop is doing a little bit of redundant work here. I could skip over the first index if I wanted to by using indices, but I'm not doing that. Maybe one extra operation isn't the end of the world. I try compiling, and I run, and there I go. So I've now been able to untangle this, to decouple the overall operation of accumulation from specifically how I am accumulating things. This is another thing that is found in the standard library. The standard library contains Std Accumulate that does basically this, although it can iterate over anything, not just vectors of ints. And like in the previous video, I should of course note that you could use templates in various ways to generalize this function further, but of course, since the standard library provides it, you may as well just call that. The key thing is you should understand you could write such a function yourself, because there's no such thing as magic, and it's these functional features that allow us to mix and match the inside operation with the outside logic.